Hello, I'm Richard with EV4U. In this video, we'll discuss wiring, switches, relays, and AC circuits. So let's get started. Switches are used to turn things on and off or switch from one device to another or from one state to another. The most basic switch, one that turns something on or off, is called a single pole, single throw switch, shown here. Another type of switch is a single pole double throw. In the EV world, we use this type of switch to select forward or reverse, and it can be used for a number of purposes. Another commonly used switch is the double pole double throw switch. The two throws are connected in this example, so both are switched at the same time. Let's talk about switch terminal identification. Your power source will come into the switch at the common terminal, and then you have the normally open or normally closed terminal. And in a single pole double throw switch, as this example is, the normally closed, that's the default. That's the position that the switch is in until you activate it, and then it would close the normally open. Switches are rated by their voltage and current capacities. There are different ways to activate a switch: push button, toggle, lever, slide, knife switch, rocker, pressure, many more. Now let's talk about relays. First, what is a relay? Well, a relay is basically an electromechanical switch, or in the case of a solid state relay, it's an electronic switch. A basic automotive relay is a switch that is activated by an electromagnet. When the coil is energized, it creates an electromagnet and activates the switch.
An electromagnet is basically a coil of wire around an iron core. And we're going to kind of replicate that now in a very simple way. I've taken a nail and wrapped some insulated wire around it. And in my circuit I have a little light bulb here to show you that the power is on. So we're going to connect it to our battery. Our light is on. And let me move into the frame here. A couple little paper clips. Now, this is a very weak one, but you can see I can pick up the paper clips with it. Let me show you another one. This is from inside of a relay. Here is our coil of wire, and there's our core in the center there. You can kind of see it right there. And so we're going to run current through our coil of wire, and that induces a magnetic field into our our iron core. And that in turn then is going to attract this piece right here, this piece of metal, and in doing so it's going to close the contacts. Let's see if we can get a close up of this. And so that's what will happen. We'll show this connected to power a little bit later on. I'm just moving it by hand, but that's how it works.
Here's a diagram for a single pole single throw relay, and here's a diagram for a single pole double throw relay, and here's the diagram for a double pole double throw relay.
Okay, what we have here is a little demonstration board, and so what we have is, this is our positive line coming in from our battery. It's going to go through our little switch that we showed you a minute ago. It goes through the switch and to this one right here, which is going to go through to our light bulb and to our negative side over here. So when I flip the switch, the light comes on, flip it, it goes off, on, off. Single pole, single throw. Now, let me show you an example of the single pole double throw. Okay, I still have our single pole single throw switch set up. So when I switch it on, our green indicator light will come on up there. It's also going to provide power for our single pole double throw switch here. The red lead being our positive, going to our common. And then one position will come over here and go to a green light, and the other position will go to a blue light. So depending on what position I have this switch in, either the blue or green light will be on. So we're going to turn on our single pole, single throw here. And we can see our green indicator light came on as well as the blue, which means when I switch this to the other position, the green light will come on. So one switch is controlling two circuits that run on a common power. So that's single pole, double throw. So let's take a look at the corresponding relays, because they're going to have the same features. So let's take a look at the one we looked at earlier. This is, get the camera to focus on this thing. This is a single pole double throw. This top contact, that's my normally closed. When the electromagnet is energized, it will close that one. Our normally open will become closed. And so this is the bottom side. And so we're going to have two terminals, which are our coil. So we're going to have a positive to the coil and a negative to the coil. Then we're going to have a common to the switch, and we're going to have a normally open and a normally closed. So this is a standard automotive style relay. We can tell right away that this is a single pole, single throw, because it's got our two coil contacts and or connections and our two switch contacts. They have a schematic on them typically, and if not, they have a printed spot on there which will give these numbers, which we'll go over in a minute. And there's kind of a standard for listing and labeling these type of devices. So let's connect this. So this is our power coming in here, and this is our ground over here, and then this will be our power going to the one to our common, and then this goes to one of our lights here, which we're going to use for showing that operating. And so now I'm going to flip the switch. Our green indicator light should come on, and then whichever one of these I'm connected to, it looks like I'm connected to the green one. So, whoops, I disconnected the battery. Connect our battery back up. Now she works. That's just a single pole, single throw. Now let's take a look at the double pole, double throw. So here's that double pole, double throw that I showed you before. It comes in a housing just like this one does. We've just removed the housing to show you the inner workings. So here we have our two coil connections. So we're going to connect from our switch to our coil, and then we're going to connect the other side of the coil to our ground side over here. And now we have a common, which our power will go to, and then we have a normally closed and a normally open, which will connect our two lights to. So there's the one light, here's the other. Now, let me see if I can adjust this so that we can see this work on camera. And I'll zoom in on it more in a minute. Hook my battery back up. And so our normally closed is already operating. flip my switch to energize our coil and our relay, showing that we have power going through our switch here, and the relay then turned on. Our other light would turn off the relay. There we go. That's our single pole double throw relay. Okay, I'll let you think of different applications for that. But let's zoom in on this so you can see it working. I'll zoom in on so you can see it a little better here. Okay, here we are zoomed in on our relay. The relay's off. Our indicator light is off. Our one light's on. See if I can get these there without covering things. Okay, let's see if we can focus in on that just a little bit more. But you can see the electromagnetic pull it in, see the contacts, see the switch operate. Okay, let's look at another example here. This is a double pole, double throw relay. You can see the contacts in there. You can see that this one right here, that's your normally open. This one right here is your normally closed. You can see this wire runs across over here. This is your common. And then these two in the very back, these are what go to the coil. And you can actually see through the case and see all that. Much easier to do so in person than it is on camera, but you can see the coil there, common, normally open, normally closed. And so you got one set on one side here, so basically it's two single pole double throw switches on either side of each other. But like I said, they're on the same little lever, so they operate together in tandem. So when one set switches, the other switches also. Well, a logical question would be, why use a relay? Well, a relay can be used as a remote switch or to isolate circuits. You can use a low voltage, low current circuit to switch a high voltage, high current circuit. Or you could use a DC circuit to switch an AC circuit. And there's many uses for a relay. Things to consider when choosing a relay. So we're going to need to consider whether it's going to be used for AC or DC. There's the coil voltage. What's the voltage and current required to activate the coil? Another consideration is the switch type. Single pole, single throw, single pole, double throw, etc. And then there's the contact rating. And so, what voltage and current can these contacts handle? So those are things when purchasing a relay you would need to consider. Here's an example of a typical automotive relay. It will have a 12-volt DC coil, and it will be a single pole, single throw, or single pole, double throw, that type of thing, with typically a 30 or 40 amp contact rating. So there's a standard to which these are configured. So you can see the terminals, and there's this diagram showing you a legend of the terminal identification. The terminals 85 and 86 are the coil, and sometimes they'll be polarity specific, but many times they're not. And then terminal 30, that's the common, that's the power or your source. It goes into your common, terminal 30. And then terminal 87 is a normally open. Now, if the relay's a single pole, single throw, you'll just have 85, 86, 30, and 87. If it's a single pole double throw, there's also a terminal 87A, which is normally closed. Now a few words about wire, cable, and connectors. Wire and cable are available in many different forms, sizes, and types. But first, what's the difference between a wire and a cable? Well, typically speaking, a wire is a single electrical conductor, while a cable is a bundle of multiple wires, multiple conductors, encased together within a protective sheath. There are solid strand, multi-strand, braided strand, insulated, non-insulated, solid color insulation, multicolored insulation, and you have very fine wire to very heavy cable. Lots to choose from.
Which you choose will be based on the application.
Be mindful of the wire, and mainly the size of the wire, because using undersized wire for a certain load can cause a problem. And so let's talk about wire. So this is a piece of single strand wire. This is typically used in, building construction, residential wiring, braided wiring. Here's an example of a braided wire. So you can see that the lower the number, the larger the diameter, larger the gauge. So 6 gauge, bigger than 10, bigger than 14. And this, of course, much larger. This is double aught.
Wire and cable are sized by gauge, and I showed you some examples. Remember, the larger the gauge number, the smaller the wire diameter. For instance, 12 gauge wire is larger than 18 gauge wire, and 6 gauge wire is larger than 12 gauge wire, and so on, like I mentioned earlier. The larger the wire, the more current it can carry, and the lower resistance per given foot. For example, a 16 gauge wire is rated at 5 amps for 15 feet. If you needed to carry the same current for a greater distance, you would need a larger gauge wire. For instance, a 10 gauge wire can carry 5 amps for up to 50 feet. If you use too small a wire for the load, the wire can get hot and cause problems. There's charts available on the internet that provide the current rating of the wire based on its type, size, and length. The resistance varies based on the size, type, and length of wire. For example, the resistance of 10 feet of 16 gauge wire, this is copper, is 0.0396 ohms. And for 10 feet of double aught cable, the resistance is 0.0000762 ohms. So a lot less resistance for the double aught cable, the same length as the 16 gauge cable. The larger the wire, the less the resistance per given length. Again, the type of wire, braided, heavy braid, fine braid, non-braid, as well as the wire material, such as aluminum or copper, all determine resistance per length of the wire. Greater resistance, the lower the current capacity. So speaking of resistance and current, this is a good time to mention Ohm's law. Ohm's law is named after the German physicist George Ohm. Ohm's law is important to know when designing and working with circuits, because Ohm's law gives us the mathematical relationship between volts, current, and resistance. If we know any two of the elements, we can calculate the third using Ohm's law. Here are the mathematical equations. E, voltage, is equal to current times resistance, and current is equal to voltage divided by resistance, and resistance is equal to the voltage divided by the current. And E originally stands for voltage, but originally came from electromotive force. I for current originated from I being intensity, and then of course R for resistance, which is measured in ohms. So voltage, current's measured in amps, and resistance is measured in ohms. Getting back to wire, cable, and conductors, using different insulation colors can help identify and keep track of your wiring. Remember, when routing the wiring, leave a little slack or a bend that will allow for the wire to expand and contract, because whatever you're securing the wire to may have a different coefficient of expansion and contraction, and we don't want the wire getting pulled loose in some manner. All of your wiring and cables should be secured so they don't rub or wear against any surface or object. Also, remember not to run wiring near anything that gets hot or in a fashion where it may get damaged. When passing a wire or cable through sheet metal or any other surface that could gouge or damage the wire, be sure to use a grommet or a cable gland net to protect the wire from damage. You should terminate wires or cables with a connector or a lug. This ensures a better and more reliable connection. And of course, it depends on the type of wire and the type of connection. Connectors should be crimped on, not soldered, especially for mobile applications. I recommend using terminal posts or terminal strips for connection points. Terminal strips aid in troubleshooting and make your setup more modular, which makes it easier to change or replace a component. There are a variety of different tools in the market for crimping cable lug. Remember to use the right size of lug with the correct terminal hole size. Route the cable before crimping on the lugs to confirm the lug orientation on the cable, especially if you're using large wire or cable. They'll have an orientation to them because they'll come off of a spool. Now let's talk about alternating current. Alternating current, AC, is a type of electrical current that periodically changes direction and magnitude. And if you watched our previous videos, we've talked about this before. And in the US, it changes direction at 60 hertz, which is 60 times per second. It is the primary way that electricity is delivered to homes and businesses and is used to power many household appliances. In a basic AC circuit, you'll have 3 wires. And again, everything I'm talking about is US only. I'm not familiar with the standards in the rest of the world. But in the US, a black wire is the hot wire, a white wire for neutral, and a green or bare copper wire for ground. So looking at this circuit, the black wires are hot, yellow or neutral, and green is ground. And shown are 2 circuits protected by circuit breakers. One circuit is for the light controlled by a switch, and the other is for an outlet, but they both go through a circuit breaker to protect that circuit. The hot wire, or the black, connects to the load. It's also the line which is switched. The neutral wire is the return. The ground wire is for safety and protects you against a short of the hot or neutral lines to a metal appliance. Remember, electricity follows the path of least resistance. You never want to be the path of least resistance. NM cable, or non-metallic sheath cable, is the most common type for home electrical wiring, also known as Romex cable, after the most popular electrical wiring brand name. The NM cables contain 3 or more individual conductors wrapped together in a sheathing, which is a flexible plastic jacket. A 2-wire NM cable contains 1 black wire, 1 white wire, and a bare ground wire. So let's talk about a couple of basics like an outlet and a switch. The proper wiring for an AC outlet includes those 3 wires: black for hot, white for neutral, and green or bare wire for ground. The black wire connects to the brass screws, and the white wire connects to the silver screws, and the green or bare wire connects to the green screw terminal on the outlet, as shown in the photo. 14 gauge wire is appropriate for most 15 amp circuits. Wrap each wire around the appropriate screw in a clockwise direction. Here is an outlet polarity and configuration chart, again US, and you'll see, for instance, the NEMA 15 or the NEMA 5-15 common household outlet here, and then you can see different ones, and you can see how they change: 15 amps, 20 amps, 30 amps, 50 amps, so forth, and some specialty ones, all the different configurations. Some are 120, 240, some are only 240, and some are only 120. Good reference chart. Now let's talk about the common light switch. The proper wiring for a light switch, again, you're going to use those same 3 wires, that Romex wire, and have the black hot, the white neutral, and the green or bare for the ground. So the black, the hot one, connects to the brass screws. One coming from the source will go to one screw, and then the other one will go to your load, the light or whatever you're switching. The white, the neutral, continues on to the load. It's not broken by the switch. Only the hot is switched. The green or bare wire, again, will connect to the ground screw on the switch. It'll also continue on. Your ground will go to the light receptacle or whatever it is. Wrap each wire around the appropriate screw in a clockwise direction. You want to tighten the screws securely, and recommend that you use the screw terminals instead of those plug-in connections, as they're more reliable. Not as quick and easy, but they're more reliable. Light switches are typically placed 48 to 52 inches above the floor, and there's a standard for outlet placement and everything else. This is not about training you to be an electrician. This is just to give you an introduction to some of the basics. So appreciate your watching, and if you enjoyed this video, please like and subscribe, and I hope to see you next time.